Okay, so welcome back to another video. So we have a definite integral from 0 to 1 of a floor function of 1 over x, and then the negative 1 degree as the reciprocal, and then dx. So I could just written this as 1 divided by the floor of 1 over x. In other words, if you want to be a little bit conventional and be nice with the writing, but however way you want to write it, doesn't matter. But as we know, with floor functions, typically the way we want to solve this in definite integrals is split this into a sum of integrals. But from one, we would have that this is from 0 to 1 instead of like a 1 to infinity, which would typically, in that sense of fashion, would make things a little bit easier to work around with. So, but with 0 to 1, we actually have to carefully like break this interval up if we, using, of course, with the definition of floor functions, and then utilizing that to convert that into as an infinite sum of integrals, but split up in terms of where in each sub intervals is actually treated as a, like a rational number instead of integers, since again we're doing this from 0 to 1, so completely a different type of scenario. So with that, nothing much to be said, so let's just jump right in. So let's notice that if our variable for x is actually in between the interval from 1 over k plus 1 and then 1 divided by k, that's actually inclusive, then we see that if I were to take the reciprocal of 1 over x, then we actually switch the bounds. When I say switch the bounds, that means, in other words, we have that 1 over x is in the interval, so inclusive k and then to k plus 1, which is nice since that's actually, if you look at this in situations of floor functions, that's how the floor function is defined to be in the specific interval. It's inclusive and non-inclusive towards the right side of the interval. This can also further imply that we can now say that we can let the floor of 1 over x equal to k, for, of course, I forgot to say, k is some integer. And so further implying we can now write this as 1 over k to the negative 1, the reciprocal of that. In other words, it's the same as 1 over k, such that for x is in the interval from 1 divided by k plus 1 and then to 1 over k inclusive. So this is nice that we can actually construct a new integral in terms of a substitution, not necessarily in a sense like acting as a use substitution. So with this, let's actually write our new integral in terms of another meaning. So with this now we have let me start off with just 0 to 1 of our our given. So the floor of 1 over x and then inverse, or the to the negative 1 dx. Or in other words, we can also put this in terms of a limit. So I can write this as the limit as n approaches infinity. So we have that this is going to be from 1 and then this is going to approach 0. So I'll write this in terms of 1 over n of, now we have the same integrand. So again, it's just still just writing the different notation for the bounds. Now let's actually put in everything for, in terms of everything of the new, well, not really the new variable, but in another way to rewrite the expression of the integral. So in other words, we can write this in terms of a limit, but now let's actually put this back as a sum. Let me first put this as a partial sum. So from k is equal to 1 of negative 1, and this is the way we want to write it this way, because if we put this in terms of of our new bounds from 1 over k plus 1 to 1 over k, so we have to make sure we have to write the intervals correctly, make sure that we're actually following the same thing as it's given. So with this, so we have 1 over k plus 1 to 1 over k of 1 over k, and then multiply, and then, well, not multiply, but times dx. And so you can see that if you were to each plug in those indexes, so we have k is equal to 1, so we have 1 over here, then 1 over 2, then start up with k is equal to 2, so 2, 1 over 3. So we see that we're breaking up this bounds from each time that these sub-intervals actually decreases, and I'm plugging this back to negative, or n minus 1, so I have 1 over n minus 1, and then this is going to be 1 over n, which is nice for what is rewritten from over here in terms of the limit, so that's great. So all this, now we have that this is the partial sum of from n, or k is equal to 1 to n minus 1 of, now 1 over k is just a constant and we're integrating in respect to x, so this is just x divided by k. Evaluate this from 1 over k to, and then 1 over k plus 1 to 1 over k. And then easily you can achieve this and see that we have this following rewritten sum. k is equal to 1 of 1 divided by k squared, then subtract 1 divided by k, then multiply by k plus 1. And we can just, so far, in other words, we can say that now what we have is the limit as n approaches infinity of this partial sum of n minus 1, and n minus 1, well, again, it's going towards infinity, but we keep it in this conventionally speaking. So 1 divided by k squared, then minus 1 divided by k times k plus 1. Okay, and let's actually, for now, put this back. And so we have that this is now we have in terms of the infinite sum. So k is equal to 1 to infinity of 1 over k squared, and then subtract 1 over k times k plus 1. Let's actually split this in terms of using some linearity. So we have a difference of sums. So the infinite sum from k is equal to 1 of 1 divided by k squared. I think everybody knows what this value is, but let me get to that. Let me finish writing this out first before I continue forward. So infinite sum from k is equal to 1 of 1 divided by k, and then k plus 1. The rest of the work here to evaluate is actually pretty simple from here. As I said, this infinite sum's notably known for the Basel's problem, so we actually know that the sums of that is actually just going to equal pi over 6. So at least that's out of our way that we need to evaluate. So the last thing we have to calculate is this partial sum over here. So let's actually fix that. With this, we know that we can actually apply some partial fraction decomposition over here. So let me put a little star, just put this. So we, if we apply this, so we have that 1 divided by k, then k plus 1. Applying partial fraction decomposition, we'll actually have the following. So we'll have the infinite sum from k is equal to 1 of 1 divided by k, and then we subtract this with 1 divided by k plus 1. And actually, you'll see that this is actually in a form of a telescoping series. Since if you plug 1, then we have 1 minus 1/2, plug 2, 1/2, then minus 1/3. Keep going, so on and so forth. Everything from the first and the last terms are only going to remain. So if you were to take this up to infinity, so that would have to mean that this is actually just going to approach, the whole series actually converges to just 1. So that means this is going to equal 1 over here. And so basically we're just done. So that means the given integral is going to just equal pi squared divided by 6, and then subtract 1. And then just like that, we have finished the simple calculation with the floor integral of the inverse, or the reciprocal. So there we have it, nice and simple. So yeah, that's pretty cool if you ask me.